Are you going to upload a study guide to Whiteboard?
Is that your home by any chance? Yeah, double check it. I can't tell the handwriting.
Wait, did you look at it like this?
Okay.
That handwriting looks really familiar.
All right, let's go ahead and get started on our final review. So kind of like I did for the midterm, my plan is to go over what's going to be on the final, do some problems that are kind of similar to what you'll see, and hopefully that will be that. So of course, first of all, check your grades. So they should mainly be up to date as of now. So the only thing I haven't put in there is the lab final. So I've kind of graded them, but I need to put a final score on them and actually put it into the grade book. But otherwise, everything should be in there. So double check that things are correct, you're not missing assignments. I think I have all the homeless papers claimed, but we can always revisit that. And so let's look at the final. So the final, as it stands right now, has 8 multiple choice questions. And then the rest of them, so there are, I'm going to say 16 questions total, plus a bonus question. So we'll go over all those. So free response. So let's see, I won't say too much about the multiple choice, just kind of be familiar with like the same colligative properties that we've been talking about. So that's on your multiple choice statements, right? Something about pH probably, conducting electricity. So let's write all that. So colligative properties. So basics of pH. Conducting electricity. So right, that basically is just distinguishing between molecules and ionic compounds. Precipitate mixtures. So determining, do 2 things precipitate? A little bit of gas laws type of things. Those salts, whether they're acidic, basic, neutral, that's a multiple choice question. A little bit about Le Chatelier's principle. So that pretty much covers kind of the multiple choice. And so now let's do a practice. Sorry, it's flipping around. And so the midterm, or our final, starts us off kind of with our equilibrium expressions. So let's see if we can remember, what was that? How do we write that? So write the equilibrium constant. So what if you have this reaction? So 2A plus 3B gives us A2B3. So write the equilibrium constant. And then we'll say find K at equilibrium if the concentrations are All right, so see if you can find the equilibrium expression, and then once you do, find the actual value given those equilibrium concentrations. So A is 0.22 molarity, B is 0.33, and A2B3 is 0.11. So I'll give everybody a few minutes to try that one. So do we get an answer for the equilibrium expression, how to write that at least? So not the numerical answer yet, but just what did that mean to just write kind of the equilibrium expression? What do we do? Yeah, so it had that general products over reactants, and then what was kind of the key? We had to do something as well. Yeah, so raise it to the power of the coefficient. So exactly. So then this ended up being A2B3, and then coefficient 1, so to the power of 1, which I'll just leave. And then over our reactants, so over the concentration of A squared times B cubed. So that was our expression. And so then all we have to do is plug in these values. And of course, remembering to cube B and square A. So I'll rewrite it for a second. So now plug in. So we have 0.11 over this 0.22 squared times is 0.33 cubed. And so now y'all can double check my math. So divided by 0.22 squared. Oops. Divided by 0.33 cubed. Do we get K of 63 for our, once we plug in these numbers? This is what people got. Did I do calculator error? Okay. Yes. All right, excellent. So then our K at equilibrium is 63.2. And remember, right, this was unitless, we said. So it just tells us who is more favored, products over reactants. So looks like our products are favored. Questions on that one? So now let's do some gas laws. So now we have a sample of nitrogen gas is in a container at 5.4 liters and a temperature of 72 degrees Celsius and a pressure of 5.35 atm. And so it just asks for how many moles of gas and what is the mass. And I'll blow this up a little. So how are we doing on this one, or what formula was useful? Yeah, so you do PV equals nRT. So that would be the way to do it. So PV equals nRT. And so we had volume. Let's see. We have pressure. So this looks good. Volume, pressure. And then what's the caveat with temperature? Excellent. So then we have to add 273 or 273.15, depending how you're feeling. And then what was R? What was that number again? 0.082. You put 8206. You can also round to 0.0821 either way, so that's good. So that's just our gas constant in all those units. So now we just have to solve for moles, so we could rearrange and plug in pressure times volume divided by our gas constant. And then 72 plus 273, so about 345 there. And so what did people get for N? Any brave guesses while I slowly punch this in apparently? 2, 1. So people got this number then, sounds like? So about 1.0, I'll round it to 0.02. So moles of nitrogen. And then the last little bit was what is the mass? So what do we have to do to go from moles to mass? Yeah, multiply by our molecular weight. So 28 for nitrogen. So moles of N2. We'll go to mass. So 28 grams per mole. And so I get like 28.6 grams roughly. Excellent. Questions on this one? Remember, ask questions if you need, otherwise we'll just keep moving along. All right, so the next type of question that we have on the exam is a limiting reagent problem. And so let's set it up. And so first we have this problem of silicon tetrachloride reacts with water to give us acid and silicon dioxide. And so the first step is to just balance it. So take a few minutes and try to balance it first, and then I'll give out the rest of it. Yeah.
Okay.
Do we have coefficients yet for the balanced equation? Ethan, do you have a guess for us?
Is it 2H2O, 4HCl, and that's it.
Yep, that looks good to me. All right, so now that we're all at least on the same starting position, so go ahead and try this. The second half of how this question will go is, so given that you have 7.11 grams of water and 8.93 grams of our silicon tetrachloride, what is the limiting reagent, and then what is the amount of silicon dioxide? So I'll give people a few minutes to work on that, and I'll go over it. So let's hear how everybody's doing. So what did we do first? Olivia, how did you start this? Let's see, someone want to help? Did people try this? Did we get lost? Where are we at? So grams to moles, so let's do that. So we have gram amounts here, so we know we need to go to moles. And so let's just focus on water first. So I'll start with water. And so we had 7.11 grams of water. And so if we want to go to moles, we need to divide by our molecular weight, so about 18 grams per mole. So then I get 0.395 moles of H2O. And then what do we do with this information? So I have moles of water, so then what do I need to compare to? So mole ratio, so good. So if we care about our silicon dioxide, let's look at water and silicon dioxide. So they're in a 2-to-1 ratio. And now let's find moles of silicon dioxide. So again, for every 2 moles of water, we have 1 of silicon dioxide. And so we can leave it in molar amounts for now. And so this is divided by 2. So then it looks like we have 0.1975 grams of product, or moles of product for the first one. So is that what everybody got for at least the water portion? Questions?
So did you divide 1 by 0.395?
I did 0.395 divided by 2.
Oh, okay.
Yeah, because you just want to multiply it by the ratio, or in this case, it ends up dividing. And then note too, right, how your moles cancel, so that kind of helps.
Wait, but if the 0.395 was moles of H2O, then how come it got 1.975 moles of silicone?
0.1975,
Yeah.
because they're in a 2-to-1 ratio, so you can only make half.
Oh, okay.
So then, yeah, so you just divided, right, divided by 2 gives you that 0.1975. Does that make sense? So then let's repeat that, right, for our silicon tetrachloride. And so now we just have to repeat. So mass, and then what's our molecular weight of silicon tetrachloride? I heard, yeah, 168, 169, so somewhere around there. I want to say it's 169. Can't remember if it's 0.9 or 0.4. 169.9? Okay, we'll go with that one. 0.9, or at least somewhere around there, grams per mole. 8.93 divided by this. Oops, sorry. Typo there. Try that again. So now I have that we 0.0525 moles of silicon tetrachloride. 0.05 to, I'll round it to 6. And so where do we go from here? Yep, so exactly. So we'll have to go back to a mole ratio. So this is in a 1-to-1 mole ratio. So this is at least slightly easier maybe math-wise. So for every 1 mole of silicon tetrachloride, we get 1 mole of silicon dioxide. So then we would have 0.0526 moles of our silicon dioxide. And so now comparing these two answers, so which one is our limiting reagent? Yeah, so our silicon tetrachloride, and so this is our limiting reagent. And so now let's go ahead and figure out the theoretical yield given our limiting reagent. And so we just need to convert this to grams essentially. So did we do that? So now convert 0.0526 moles of silicon dioxide to grams. And then I think, what'd you guys get for the molecular weight of silicon dioxide? 60.1, so that sounds good. So now we can just multiply it. Grams per mole. So times 60.1. And so I get a theoretical yield of about 3.16 grams.
All we need to do is change it to grams.
Yeah, so we just did our moles to grams there at the end. Questions on this one?
So that answer was the theoretical yield?
Yeah, 3.16 is the yield.
For the, yeah, so for the theoretical yield, we don't have to like change it to percentage or anything. It's just the.
Oh, yeah, because I didn't put anything else. Like, I didn't ask, like, we got this in hand. So if it just asks for theoretical yield, then it's like 100%. But then, like, percent yield, right, I have to tell you something else. Like, oh, we actually got this amount. All right. So let's do another, oh, sorry. Go away. Let's do another pressure volume one. So we have the initial volume is at a pressure of 2.88 atm and 8.63 liters. What is the volume if the pressure is increased to 5.21 atm? So what formula do we need for this one? Yeah, excellent. So P1 V1 equals P2 V2. And I'll throw this one on there, just the full one, so you can always have it here for reference. And right, we can, of course, derive the P1 V1 equals P2 V2 since it didn't mention N, so that's probably held constant, right? No temperature change, so all those go away in this case, leaving us with that. So excellent. And so now we just have to plug in our initial conditions and then, of course, figure out our new volume. And then double check your units. So, right, it didn't matter as long as they're the same. So ATM, ATM, that works. So we'll be calculating in liters. That's all good. Now we should have something that looks like this, so we don't know volume. We have our new pressure though. So now we'll just do our math. So 2.88 times 8.63 divided by 5.21. And so do we all get 4.77? Excellent. So our new volume is 4.77 liters. Questions on that one? Flying through these. All right, the next ones we'll do will be more pH. So let's try. Sorry, I'm seeing where I want to start us first. So let's just do this one. So what is the molarity if you dissolve 10.91 grams of HCl and 1437 milliliters of water? And so I put the second half of the question up there, but
Is there supposed, was it, did you mean 14.37 or did you mean 1,437?
yeah, 1,437. So how do we figure out molarity? What did we do for this one? So molarity you said was moles over liters. And so how do we get moles out of this then? So grams to moles, so let's do, so 10.91 grams. And so divided by, what'd you get from the molecular weight? 36.46. Excellent, like this tag teaming here. Let's see, 10.91 divided by 36. So then I have about 0.299 moles of hydrochloric acid. And so now you're telling me, well, let's do moles over liters. So we had to convert this to liters. And so now we're ready to solve for molarity. So 0.299 divided by, so just converting this to liters, so 1.437.
Would you just divide it by 100?
By 1,000. So divided by 1.437. And so I get a molarity of about 0.208. So I see that's what a lot of people got. So 0.208 molarity. And then do we have a chance to find the pH yet? Okay, I'll give people another few minutes to look at that. So how do we get pH then? Oh, yeah. Because we have to convert milliliters to liters, so then, right, there's 1,000 milliliters in 1 liter, so that's why. So what was the formula for pH? Do people remember? So negative log of our hydronium concentration. And so what do we need to plug in then from this number? What is this equal to? Yeah, this number, right? So, right, we have acid, so this is our acid concentration. We found it. And so this is the same as our hydronium concentration. And right, this works out because it is an acid-making species. It's a strong acid. And so right now we just need to plug this into there. So negative log of 0.208. And so let's see what that gives us. And so pretty low pH of 0.68. And that makes sense, right? Because it should be acidic. And sounds like we made a fairly acidic solution there. So low pH. Any questions on this one? All right, so now let's essentially do something similar but different. So now, how does this work? What is the pH if we dissolve 0.766 grams of sodium hydroxide and 956.7 milliliters of water? So how do we get the pH? So I'll give people a few minutes to work on that one. see, do we have answers for this one? How do we solve this one? So grams to moles, so let's do it. So 0.766 grams, and then what's the molecular weight of sodium hydroxide? 39.997. That sounds good. So let's see. So 0.766 divided by 39.997. And so then did you get this many moles? So about 0.019. Excellent. And what do we do with our moles now?
Put it over liters, so it converted the milliliters to liters.
Excellent. So now we have 0.9 liters. So then you just went ahead and divide to get molarity. So 0.01915 divided by 0.9. So then I got a 0.02 molarity. And so now what do we do with this number to get to pH? So put it in for negative log, except what are we solving for with the negative log? So what did you put it into? What formula exactly? So what did you solve for?
I just thought that was the next.
It is, but P what? pH, but we can't just plug this into pH, right? Because pH is a negative log of hydronium, we said. But right now we have hydroxide concentration. Well, what's a pretty similar looking formula? Yeah, POH. So, right, that one doesn't quite work for us. But we could solve for POH directly. So that's the negative log of our hydroxide. So now that works. Okay, so now we can plug that in. So let's go ahead and do that. So now we're solving for POH. So I get a POH of 1.69. And so now what can we do from here? So I have my POH. It's another good formula. Yeah, so 14 minus POH equals our pH, perfect. And right, she just got that from our pH plus POH equals 14, so that's standard. So rearrange to give you that, so that looks good. So 14 minus that. So then we should get a pH of about 12.3. It sounds like that's what people got. Excellent. Questions on that one.
I'm confused on why you use the pOH equation instead of pH.
So in this case, it's because they'd given us sodium hydroxide, right? So then we didn't have any like H plus concentration, because previously, right, we were given H plus because they gave us acid. But then since they gave us the hydroxide, we had to start with the pOH and then use that relationship to get pH. So let's do another type of problem. So if, oops, sorry. So if you dilute 10 milliliters of a 1.11 molar hydrochloric acid solution to make 1.56 liters, what is the pH? how we doing on this problem? So what was the first step? So Bethany, what did you do for this one?
I was confused on where to start. Because like in my head, since we have the molarity, I was thinking you could just punch it into the pH equation, the negative log H3 of plus, but it gave me a negative pH.
So let's see. So the only problem is, right, so we started with this, right? But it says that we diluted it. So we need to figure out, so we might have a new molarity. So what?
We set it up as a ratio and then.
So you could do a ratio, or what's that? There was like a formula.
It's the C1V1 equals C2V2.
Yeah, so C1V1 equals C2V2, or you could use the M, so either way. And so, right, it doesn't matter. So we do have a little issue in that we have, right, milliliters and liters, so we have to pick a unit here. So might as well just make them liters.
On the test, will it matter which one you can?
No, you could have converted it to milliliters. Yeah, as long as they were the same, but I was a little tricky there that I didn't give you the same unit, so you had to either pick one. But yeah, it didn't matter. So now we have 0.01 liters, right? And so now this is our initial volume. This is our C1. And so, right, we're going to find our new concentration with our new volume. So now we can plug that in. And we'll be solving for it in molarity. 1.56 liters to match with this in liters now. Divided by 1. And so do we get X is 0.007? So I see some nods. And right, so this is our new molarity then. And so now we can go ahead and plug then this into our formula. And right, it is HCl, so it's appropriate to go to the pH equals negative log of hydronium. That matches. That's what we were given. And so then I get a pH of about 2.15 roughly. I see some more nods for that one as well. Excellent. Questions on that one? All right. So we've pretty much made it through the whole exam. So we have two more questions that we'll go over. So your last official exam question is a energy diagram. And is this, oh, no, sorry. Let me just type it out. So sketch a labeled energy diagram for an exothermic reaction with a delta H of -10 kcal per mole and a activation energy of 15 kcals per mole.
What does the EA stand for?
Activation energy. But on the exam, it's just going to be that little EA, so you have to know that. So how are the sketches coming? And so I'll kind of go over what your sketch should look like. So it doesn't really matter where you start, but you just want to label, right? You have your reactants. And then, so in this case, right, you were given an exothermic reaction. So products are going to be lower in energy. And, right, your delta H tells you the difference. So in this case, it's 10 lower. And so you want to label that. Right, so delta H equals 10 kcal, and so down here is your products. And so now we're missing, right, the middle part, the transition state. And so it tells us the activation energy is 15. So we need to label something here of EA equals 15 kcal. And you can label this, right? So this is our transition state up here. And kind of connect the dots now. So reactants, right, they go up to our transition state with our activation energy. And then, of course, back down to our products. And again, in this case, it was exothermic, so it was lower. But just pay attention for your exam, right? I might give you endothermic. Who knows what will happen. And then you want to also label your reaction diagram. So energy and reaction coordinate. So those are your labels. So labeled axes, and then we got everything. Reactants, products, right? Transition state, EA, and delta H. So make sure you have all those parts on your graph. Questions about the reaction coordinate diagrams? Yep, and so, right, if I just switch this, yeah, I can do it in this pink color. So yeah, I'll do endo in pink, right? So same conditions, but what if I had said endothermic, right? Then we could do same sort of thing. Reactants, it could still have an activation energy of 15. So we could still write this. And then if it had said endothermic though, then we'd want to put it ending up somewhere around here and label this as 10. So yeah, so that it would look something like that if it was endothermic. So just note, right, your 10, your 15 for your activation energy. Yeah.
So wouldn't delta H be negative in this? Or what,
It doesn't matter the sign too much because it's just a difference. But yeah, if you're looking at it, it should be negative, but sometimes when we're writing it, like I'll just say the difference. And then, yeah. So when you write these, pay more attention to the endo, exothermic, and then save that negative thoughts for later in the math and stuff. All right, let's do one last problem, and that's the bonus one. Because I think you could totally do the bonus. It's not too hard. And so the bonus will look very similar to this, but not quite. So we have this reaction. You probably know my obsession with the Haber-Bosch process already. And so the delta H for this reaction is negative 600.1 kilojoules. And so right when this is given to you, and whenever, you see whatever scenario is on your exam, right, this is for this stoichiometric amount. So that's kind of the point to keep in mind, that this delta H, right, is for 3 equivalents of hydrogen, 1 equivalent of nitrogen, and 2 equivalents of ammonia. And so now the question will read, so calculate the heat evolved when 2.36 times 10 to the 4th grams of ammonia is generated. So think again about what this statement is telling us, right? I gave you a hint that it's that molar amount, that this is what it's equal to. So then what would you have to do to figure this out? Then we'll go over it. So let's hear your thoughts. Do we know what to do with this? Do we have any ideas? Remember, I said the key was this And so, right, this is for 2 moles, right? So that's telling you that this is a heat generated, right, when you make 2 moles of ammonia. And so really we just need to convert, right, grams to moles so then we can do some sort of comparison. So, right, so if we know, well, 2 moles of ammonia produces this much heat, we need to figure out, well, how many moles of ammonia is this, and then get a ratio. So let's go through that. And so we can just start off by our usual, right, grams to moles calculation. And do people remember what ammonia weighs? What did you say? 17. Yep, 17, so 17.031 grams per mole. And so now this is going to give us a big number, but so 2.36. Yeah, I'm not sure where. I was wondering that as well. Where did this? It was big, but not that big. Divided by 17.031. And so then I get about 1,385 moles or so, or 86. So moles of ammonia. Right, and then so from here we could either set up a proportion or set up a conversion factor. So if we have this many moles of ammonia, well, we know for every 2 moles of ammonia, it produced 600 kilojoules of heat. And so now just divide it by 2 times 600, and we get this many kilojoules, which is a lot. So 415,000 roughly kilojoules. And if you can also set this up as a proportion if that works. So, right, for every 2 moles of ammonia, it was 600. If it was 1386, set it over X, and you could get that same answer. Questions about that last one? And so like I said, this one is the bonus, so now that we've gone through it, I feel like everyone should be able to get it, but it's still just a bonus, so don't stress out too much. And I think that's really all I have prepared. So we've gone over all the exam then effectively, so you've seen, basically what you're going to see, so expect these similar type problems. So we can end here officially, and then I will, of course, be around for questions if people have more questions. And, of course, thank you guys for an awesome class. You guys have been fun. And I'm sad we only had 1 quarter together.